We are back with another episode of Scaling Robotics. This is a series of conversations with leaders at robotics companies who have actually scaled their fleets. We hope to democratize their hard-earned lessons to benefit the next generations of robotics companies. Cem, thanks for being here. Do you mind introducing yourself and Simbe?
Yeah, please. Thanks for having me. I lead robotics software at Simbe. Simbe, we build autonomous robots that help retailers ensure that product availability and accuracy is good at a high scale. So we help them identify like item location, which is a big deal for e-commerce and order fulfillment. We help them with shelf conditioning, basically everything you see in the store when you go in. We help them execute to a higher level than they could without our solution. The primary method of ensuring this is we have a robot Tally. Tally will go around retail stores and capture a whole lot of data from, everything from the shelves to the environment. And we distill kind of very actionable insights and analytics and data from these captures and provide both like a snapshot of the store to our customers, but also specific insights and actions that they should be taking.
One of the reasons that I'm so excited to chat with you from our previous conversations is just talking about the scale that the Simbe fleet of Tallys are operating at, and your lessons that you've learned from this kind of scale up. Do you mind telling us a bit about the fleet that you guys have scaled at Simbe? Any interesting facts about the customers or deployments or anything else that you can share with the audience?
Yeah, we've basically deployed thousands of robots across a lot of major retailers, some names that you would know, some that you might not. We operate daily across thousands of stores with basically like non-trained real world people, which I find very exciting. In addition to this, we operate in maybe like more than 1,000 cities and 10 countries around the world. So the environments we're in are very interesting, very dynamic, and very I don't want to say chaotic, but they're different than where you'll find most robots, right? So most robots that we're familiar with maybe exist in factory environments or warehouse environments. It is a very different experience altogether, being there with real world humans that are not trained in robotics. Our clients are in more or less all areas of retail. We have clients in grocery, we have clients in the club store format, farm supply, home improvement, apparel, alcohol. Basically, if you can imagine like there being a retail store, we build the solution for it, which also makes it, I don't know how much time you spend thinking about like your different retailers that you go to, but I've learned in this job that a club store is a very different environment than a grocery store. There's even like, I don't know, every time I go into a grocery store, I'm like, oh, that's interesting. Like there are hang downs there. That's an end cap. It's a very different way of perceiving that environment. But basically, we scan millions of shelves per week. We generate actionable data on millions and millions of items, and we've driven. I don't have the full data, but many autonomous miles. Let's just say.
Yeah, I think, like you said, one of the most interesting parts to me about Simbe's fleet is the fact that you guys are operating alongside real humans every day, like you said, are not trained in robotics across various types of retail stores in various countries. I know from experience going to India, the grocery stores there look a lot different than the ones here. Yeah, what are some of the lessons that you've learned from building robots that work in quote unquote chaotic environments and that operate safely alongside humans?
Well, that's a good question. A couple of big things there. One thing is it's interesting. Humans operate in a when you're around people, you operate in a way that has a lot of expectations of others built around you. So when you're in a grocery environment, you are kind of you're perceiving everything that's happening around you, but you're also making assumptions about what's going to happen next. We found that to be very important when designing our, especially like behavior and navigation algorithms. So not only that there's a person here who's standing, but where's that person going to go next? And therefore, what should I do? What should I do given that next possible action? A second thing is kind of to the point of like different store environments, right? Like one of the things that we learned pretty early on in my tenure is we have this solution that works for maybe this one grocery form factor, but when you take it to a club environment, it is very, very different. One, the way in which people behave is different because let's say you have an average aisle that's twice the size, like twice the width of an aisle of your average grocery store, and people just like exist differently in that environment, and they have different expectations of each other. And we basically found out pretty early on that the behaviors we built for this one environment didn't fully translate to this other environment. And then related to this, like the way in which you solve for these is getting a lot of data and using that data to iterate and test your algorithms. And one of the things that I think sets us apart in the current state is we have access to all this data, be it bag files or logs or just like raw analytics on a lot of very different environments. It's not just we have the data for grocery, we have the data for grocery and club and farm goods and all that, and that allows us to build a much more robust robot, I think.
Switching gears a bit, keep going back to the scale of the fleet, right? Thousands of robots. What's different about building robot software for a fleet that big? I imagine there's many trade-offs, many considerations. Would love to hear about them.
Yeah, it really changes with like orders of magnitude, right? Like one is very different from 10, is very different from 100 to 1,000 to hopefully like soon 10,000, let's say. One big paradigm shift, maybe around the 50 to 100 robot mark, is you go from this reality of like, I could always connect to the robot, fix it remotely, SSH, what have you, to, oh, like I have, let's say, 500 robots, 1,000 robots. I can't fix these remotely. These need to be like actually autonomous. And there is a lot of work between something that is 95, 98% autonomous and needs human intervention every now and then to something that needs human intervention basically never. And this applies for hardware as well. I think hardware is, kind of obviously a core part of robotics, but especially in a solution like Simbe's, where we have maybe one, at most two robots per store. The stores are distributed across a large geographic area. We kind of operate in this model. It's like we have the hardware that we have, and that hardware may be 5 years old. That hardware may be, let's say, not in the most ideal situation, but whatever the hardware is across however many thousand robots you have, you kind of deal with it. Whereas if you had 20 robots, you can kind of enforce a better kind of set of hardware. Like you can say, I have 20 robots, I'm going to upgrade the computer on 10 of them so that the fleet is at parity. That's a reasonable amount of effort, a reasonable amount of resources, and you can kind of enforce that. At 1,000, 2,000, 3,000 robots, you can't do that. So you have to work across, you have to have good legacy support. You have to make sure that your fleet operates reliably. And it's an extra difficult thing because one, you need your fleet to operate like 10 times more reliably. People tend to think like there's 10% difference between 90 and 100%. Like there's a 10x difference between like 90 and 99%, and then another 10x from like 99 to 99.9. So you need to do that. All the while you need to support legacy hardware. All the while you need to support like maybe a hardware part that is a little bit over its ideal lifespan that we just couldn't get around to replace yet. So it's a big challenge. It is a very interesting and fun challenge, let's say.
I'm already hearing the battle scars kind of in the description you
Yeah, a
just
little
gave.
bit, but the battle scars and the battles, like, it's what sets us apart. And one of my favorite things about working at Simbe is the fleet size, and that we actually make a difference in the real world. It's not one like robot that we build that is maybe a very cool R&D product. But this is a robot that we like constantly manufacture, ship more of, thousands in the field. It's also like I, I say this to people who are interviewing for us, like, this is a robot that your mother might meet. Like, I introduced my grandma to Tally in a store, and that, I think, is like, it's a very special thing, and that is because like we have a fleet of the size that we have with the reliability that we have.
Yeah, I agree. There's, I think, very inspiring to see that you guys have scaled and um, many companies aspiring to get there. And there's a lot of uh, advantages structurally that you get from being at that scale. So you mentioned a few things that are different at scale and some of the considerations you make. The first one you mentioned was on the software and autonomy side, just having to really increase reliability and squeeze out those extra nines. Can you talk about how that changes how you actually, build, test, deploy software? Is there anything else that any considerations you're thinking about because of this extra need for reliability?
Obviously, like, yes, a lot of extra considerations. I will say one thing is a stricter testing pipeline and testing discipline. The obvious part of it is like, more unit tests, more tests in simulation on bag files, etc. But this also leads us to kind of necessarily be more nimble about the software that we design. One thing that is very different with robotics as opposed to, let's say, like a SaaS company where you may have like thousands of VMs, is our robots are very much like physical hardware entities that exist in the real world. So we are constrained by a lot of constraints that you don't really have in the SaaS world. So one of these is, for example, network speed. You may be able to, how do you update a virtual machine, right? You make an image, you maybe like destroy the old one, you put up a new one, it's a 1 minute thing, and you already have the old image anyway, so you can just like, roll back in an instant as well. With the robotics, it's a little bit more difficult, especially with the robotics where, again, like, we're in retail stores, thousands of different environments, etc. So we really, really value, one, being able to individually feature flag behaviors that we can turn on and off, and also parameterize things that we can tweak kind of continuously. We don't just think about software updates as, I made this update, it was behavior A before, and that it's behavior B now. We think about it as more a continuous process. Each feature, each software update has maybe, I'm going to make up the numbers, but if there are 10 features in it, maybe 3 of them are on by default, 3 of them are off by default, and other 3 of them are kind of in between. They're on by default, but they're not on to the same extent that we want them to. And we constantly like test these. We test turning them on, and through our like data dashboards, and also watching the robot is very underrated. But we constantly like look at the behavior and try to tweak as the lifetime of the robot progresses.
Kind of what you're describing, right, is in some way A/B testing different features on the robot, flagging them. Um, my experience is that this is something that, because again, a lot of companies haven't scaled, they haven't got to experience what A/B testing really is like, right, at a robotics company. Um, what what would you say are some of the big differences? Let's compare to SaaS for A/B testing and robotics. Anything that folks should be looking at or looking out for when they're initially starting A/B testing for their fleet?
The main difference in my mind with SaaS, and I'm sure the SaaS people online will disagree with me passionately, is from the outside, SaaS feels like it is a little bit easier to dial down to maybe 5, 6 numbers. You have your like lifetime value of the customer, you have like your conversion rates, churn rates, maybe user activity. And all of those are things that you can very quantitatively track relatively straightforwardly. You have your paywall, you have your like how many people hit the paywall, how many people convert, etc. With robots, there are some metrics that seem easy. For us, like one of that is like the speed at which we cover the store, how many products we scan over an hour. That's a very easy thing to track. But there is this very intangible aspect of being a robot that interacts with people as well. Like, how do people feel around you? That is something, especially in an environment where you interact with untrained, regular, everyday people. Not necessarily quantifying the intangible, but being able to make either a quantitative or qualitative decision about it is very important. And I think it sets robotics aside a little bit. One thing for us, for example, is I could increase our coverage rate tomorrow by making the robot faster, like physically move faster in the store, right? And I believe with very, very high conviction, like all the data points, it will be just as safe as it is now. But will people feel as positively about the robot as they do now if the robot starts driving faster? There's a lot of like human robot interaction is a big field because of this. Like there's one aspect of like safety and efficiency, but there's this other aspect of you exist with other people. How do the people feel about you? Do they like being with the robot? Is the robot like is it a cute robot? Is it a big scary bad robot? All of these things are also very important, and especially when you're doing A/B testing, it's very alluring to just like put a dashboard up there, 3 metrics. You see them go up by 20%. You're like, yes, great, I want this. Like this is the way forward. But we found not always.
Bouncing back to the hardware side, you keep talking about the constraints of legacy hardware that's still out in the fleet that needs to operate, and newer hardware, and making sure that you can deploy the same software and increase performance on both of those. What does that problem look like tactically when you're designing new software and creating new updates?
We always want to support all of our robots basically with every single feature, and we try to organize it in a way that we allow the feature to exist in all robots at the same time, but maybe the feature is a little bit better or faster or works in a different way on old versus new robots. So like one thing that is so great as a kind of hardware as a service company is there are these consistent updates that we get to our customers, and we want that to keep happening. So it's important that everything works on everything. But obviously, there are some features that maybe are available in the next generation hardware that are less available in the old generation hardware. Again, the engineer in me wants to say we're going to build the most powerful computer into all of these robots, and we're going to ship them out to all existing robots as well. But kind of the core tenet of engineering is finding the compromises. So it's definitely an interesting challenge, and I think it keeps us honest and ultimately makes us build better things, knowing that it needs to support not only the new flashy thing but also the kind of couple-year-old hardware.
Have there been moments in your team's experience where you want to run some, like you said, cutting edge algorithm that assumes the latest, NVIDIA chip, and you can't? What's that feeling like when you again have to make that compromise across the fleet?
There have been, obviously, like there have been a lot of things where we're like, oh, this is the next big thing, and we would love to have it, and you deploy it on existing fleet, and it doesn't go necessarily the way you want it to. We've historically, we've approached this from 2 sides. One is, I would like to believe we write very good, efficient code, but there's always more efficiencies that can be found on hardware. So we've made some headways shuffling some things around from the CPU to the GPU and vice versa, for example, or um, looking at how the data flows through the robot in the cloud and kind of making that more efficient. Just as an example, like we discovered that we were JPEG compressing the same image twice in our process, for example. Like finding those inefficiencies and getting rid of them, it gives you another 5%, 10%. And that 5%, 10% is then things you can use for the next generation products. The second thing is that I think this sets our AI product aside as well, is in today's world, there really isn't a whole lot of things that you can't get, let's say, a Claude to do. And I think increasingly what sets like a good engineering practice from a bad one aside is, can you do the same thing with not 10% less resources, but maybe 10x less resources? So a lot of our brain power goes to, yes, like a Waymo, for example, like it navigates with 6 lasers in a 3D environment, very smooth, like almost like continuous space, right? But a lot of our, and obviously we're not driving at 60 miles an hour, but a lot of our effort goes to how do we make a 3D problem into a 2D problem? And yes, we'll lose fidelity, but maybe we're not going to lose performance. And how do we get that 2D problem, and maybe we don't need to solve that 2D problem at the 10 millimeter resolution. Maybe we can solve it at a 100 millimeter resolution and only go down to like 20 millimeters for this part of that problem. Like, how do we divide it up into chunks of like high resolution, low resolution, high fidelity, low fidelity, and basically allow us to find a smaller chunk of data that we can run the fancy thing on, rather than, big model, big algorithm, big data, go for it.
One part of the answer you just gave that was interesting to me was, with tools like Claude or just AI coding tools in general, you're able to increase efficiency by an order of magnitude. As someone who's leading a robotics software team, what other ways do you guys use AI coding tools that you feel have changed how you build, changing the need for external tools, how fast you guys can go, how aggressive you can be with the performance? What does that look like?
Great question. I think that's on everyone's mind these days. And obviously we use like a lot of AI tools. They're built into our workflow now. And there are good things and bad things about that. One thing that I really, really appreciate that I think maybe it doesn't get talked about enough is we've started building kind of throwaway one-time tools, one-time like pieces of software, which has been a pretty big win for us. Like you can just build this, 1,000-line script that tests for one thing, that does one thing for your current project, and you don't check it into source code ever, and you don't make it a production tool, but it serves as like a very good kind of cross-reference or something. Faster is a difficult one to answer, especially. One of the main reason that we work at the speed that we are isn't that we can't code fast enough, but it is that one, the just nature of the store with the connection speeds that we have and with the environment that we have, especially because in robotics, you can do a lot of simulation testing, you can do a lot of like bag file testing, you can do a lot of unit testing, you can do all those things. I still think in this day and age, like nothing beats rolling the software out to a fleet of robots, doing kind of like a stage rollout, and then going, in our case, like flying to wherever the robots are and watching them in person. That gives us still a like unparalleled view into what's happening in an environment. And that is kind of what drives our software update cadence, like the speed at which we can do a stage rollout with, actually observing the robots and making sure that our customers get the most refined and well-tested piece of software. The coding velocity has increased with AI tools, and maybe we do ship a couple more features in every release than we did before. But the speed at which the releases get out is really dependent on this level of like, stage rollouts. How do we fit in best within the operations of our clients, and how do we make sure that we have the time and resources to monitor the release as it is going out.
Um, One of the things you just mentioned there was staged rollouts. I imagine, at a fleet this big, that's really important. Doing a Canary rollout is not only nice to have, but it's critical. What does a good Canary setup look like? Was there anything you learned building out this kind of stage rollout process that's worth sharing?
Um, Honestly, nothing that you wouldn't assume, but I'm going to say it anyway. The big important thing is you want to make sure that the stage rollout you're doing is actually representative of the fleet at large. One thing that I've been guilty of before is there have been customers that I was more comfortable with, customers that I was less comfortable with. And we've had features that we rolled out to customers who are more comfortable with than the customers who are less comfortable with. But the environments there are very different. So are you really doing a stage rollout if you're staging it across like client A, B, C, D, E? Like kind of, like there's things that are similar, of course, they're all retail stores, but making sure the sample size is representative. It represents the hardware of the robots, it represents the variety of environments you have, and the timing is very important as well, especially because, again, we're a very like human overall population facing solution. Weekends are different than weekdays. Afternoons are different than morning time, and obviously like overnight traversals where no one is there is also very different. Making sure that we have the right data to compare apples to apples basically there is very important in the stage rollout as well. You don't want to do a Wednesday software release, test it for 2 days, and before the weekend say, okay, it's good.
On the tactical or building level, are there any good tools that you guys use for Canaries or anything else to recommend on this side of the house from your experience?
We've largely built all of our own tooling. We have a lot of data collection that we have on board the robot that we've largely built. We rely heavily on bag files. We also rely heavily on telemetry that we collect. And this telemetry is not only, our CPU percentage, memory usage, etc., but it's also like robot telemetry, like hard robot data. Especially things that are like what the robot is doing, what percent of the time we find very useful. If the robot isn't like standing around for too long, for example, that's not behavior that you want. Specific tools, I'm gonna give a shout out to Foxglove, which has helped a lot to like visualize our bag files and event tracking as well. But outside of that, largely most things have been homegrown, including our like logging and data collection and visualization. There have been a lot of tools that came out recently in the last couple of years. I think we were a little bit early to the game. I think robotics companies that are starting up now, they have a much more robust ecosystem with a variety of solutions to pick and choose from, because we started earlier. We built our own fleet management solution. We built our own data collection solution. We built our own telemetry solution. I think slowly, and maybe even like, not slowly, there's a lot of like very cool startups and solutions out there that you can use for these.
Awesome. So, in a conversation that you and I had before, you mentioned something that I thought was really interesting. At some point in a fleet this big, it's not about if something will fail, it's about when it will, or if it already has, finding it. And you mentioned that you found this robot that had 100 megabit connection between its internal hosts instead of a gigabit like it was supposed to. and you only discovered it when a new software release rolled out. Um, I think that story is very emblematic of what it's like to have a big fleet. Can you tell us more about this, what it taught you, and yeah, maybe how it changed your perspective?
Yeah, it is a very interesting story. We've had similar ones, as you might imagine, but over time with hardware, you develop these kind of expectations, maybe prejudices, even that there are some things that fail often, and there are other things that you're like, oh, this never fails, right? And at 100 robots, that's true. Your internal network, or at least our internal network, like it never failed at 100 robots. 1,000 robots, 2,000 robots, more than 2,000 robots. There's a point at which everything fails, and it's not because like your hardware is bad. It's not because your testing is bad. It's not because your software is bad. It's because like law of large numbers or whatever you call it. At thousands of robots, many years per robot in the field, something is gonna go wrong. There's like vibrations. There's cable impedance, whatever you have. This specific scenario, one of our software releases, we started relying a little bit heavier on our internal network than we used to previously for one reason or another. And we saw this one robot kind of fail in a way that we really did not expect. And the way in which we caught this basically is our monitoring tools started flashing an alert, and so we ended up pulling a lot of data, and our data kind of indicated that there was this like suspicious trend in our internal network that we're hitting this like cap and never going above it, but it was this very like suspicious flat line. So ultimately what ended up happening is we ended up like doing a deep dive. We figured out the internal network failure, not failure, but like degraded service, if you will. We did a selective rollback of that service that we deployed that was taking up extra network bandwidth because of the feature flagging and parameterization that I talked about. And ultimately, eventually, we ended up replacing a cable in that robot to, get it up to spec and enable the whatever new feature was as well. But the learning moment here is like, one, as you said, like at some scale, and we're certainly at that scale now, the unexpected is kind of expected. Like components that you trust fully are going to fail. Maybe 1 in 1,000 in 3 years, but it's going to happen. And then observability and monitoring, like that's super important. That's something we've invested very heavily in. But basically, you need to know when something breaks, even if it's like not a full break. This robot was never grounded because of this issue, but its service was degraded. And it's very important that you get an alert raised before your customer basically starts complaining about, oh, like, why is my service degraded? It's important that we know that before our customers do, so that we have the best kind of service. And then it's also important that, if I discover the issue and I can't do something about it for a week before we can like diagnose this to this specific cable and schedule a replacement, it's better than the issue being escalated directly to the customer, but the customer still receives degraded service. That's not something that we want. Like if there's anything we can do, no software release should lead to customer data getting worse. So every issue that the software might uncover, the software also needs to be able to at least temporarily circumvent. So those are kind of those are kind of the important bits.
And I love that, right? Like you never want a new release to impact customer service or customer performance negatively. Um, does this go back into, I think, you've mentioned before some of the things that you build a workaround into everything you do, right? Throttle logic, the flags, caching mechanisms. What does that look like? Why and just maybe talk more about again why that's so important.
We basically have in our software somewhere between like 2,000 to 4,000 parameters. Some of these are feature flags, and importantly and interestingly, some of these are feature flags that we haven't touched for 3 years. I know a lot of companies like love deprecating feature flags. To be entirely honest, it will make my code base like much cleaner. So I fantasize about this. But this has kind of two or three advantages. One, when you run into an issue in the field, you have a variety of attack vectors that you can pursue or not pursue. And in a situation like this, like I deploy feature A, right? And feature A overloads the internal network of this one robot that has a lower internal network capacity. I don't want my only option to be to roll back feature A or to roll back the full software. I want to be able to look at the 8 features that use the internal network and make a little bit more intelligent decision. Maybe I want to prioritize feature A, but I want to move my camera encoding process from this host to this other host to allow for a little bit more like extra room for this new feature. So that being able to be nimble and move things around and disable some features, enable some others, change parameters on different ones, like that's very, very important for us.
I'm learning so much here. I love how thoughtful you guys seem to be about dealing with these problems that, yeah, again, happen when you have thousands of robots. Uh, Maybe, switching gears to you in Simbe, you didn't always have thousands of robots, many, many customers. In your journey of growing Simbe into what it is today, what are some of the hardest moments in this journey that you remember?
That's a great question. I alluded to it a little bit in an earlier answer, I think, but the biggest challenge kind of early on in my tenure was scaling Simbe from a company with a small number of pilot customers and all pilot customers with similar grocery environments to multiple scale deployments across a variety of retail form factors like club and farm and home goods and grocery store. Early on in that scale adventure, in addition to building 10 versus 200 versus 1,000 robots, like in addition to all the other craziness, we discovered that we needed to learn these new environments more than we anticipated. We were kind of a little bit complacent in saying we're in this one environment, we're doing great. This two environment, we're doing great. The third one will be similar. But we discovered early on that we'll need to do more work and kind of tune our parameters a little bit better, which is also an advantage of having this massive set of like parameters and feature flags for different environments. We realized that we can't operate the same way across all environments. So basically, this led to a series of very tiring, but also very exciting and energizing visits across a lot of different places, mostly in the East Coast and the Midwest, of a lot of retail stores, hours and hours basically with a laptop watching after Tally, which I will say, bag files, Fox Love, watching those, super good, but nothing to this day truly beats like following a robot around in person. But basically in a span of a couple weeks, I watched along with our CTO and a couple other people, like tens of robots, maybe hundreds of hours, and learn more about our own product than I thought possible over like 2 weeks. And this was kind of the catalyst for us to transition from, this is a robot, this is what it does, and we'll watch it, to this is all this data, like we have bag files syncing to the cloud, low fidelity, high frequency telemetry data that we're syncing elsewhere, dashboards, alerting systems, and kind of a more structured testing platform. That was kind of the outcome of all of this, right? So we built all these data systems and retailer customer based parameter systems, all of these as a result of this, and it's made us a lot more nimble and a lot more data aware than we previously were.
Also in this journey of being at Simbe and scaling Simbe, you've had to grow the team, a fair bit. Uh, for the engineers that you've hired over the years, what makes a good robotics software engineer, and largely how do you screen for that?
That is also a great question. Um, a lot of it is similar to what makes a great engineer to begin with. One thing we value a lot is because we're not, a mega corporation with tens of thousands of engineers, we care a lot about people who are uh, independent isn't necessarily the right word. We do a lot of like collaborative projects, but people who can think about the bigger picture maybe more individually. But a larger place, you have other people to think about the bigger picture for you. And, you know, if you work for one of these large companies, someone will tell you like build this one small thing in this exact way, and you don't need to care about why. One thing that I think sets our engineers apart is thinking about the bigger picture. Like the project you're building obviously exists as a small to medium part of a much bigger whole. Uh, what are those other processes? What are the interdependencies that you have to talk about? And a good engineer, a Simbe engineer, thinks about the implicit and explicit promises that their feature makes to the system as a whole, and also to all of the stakeholders being like uh, our customers, store representatives, to our other internal teams like our computer vision team and data team, to the individual humans that interact with the robot. That makes all of the difference. Another thing is, let's say, uh, owning ambiguity, if you will. We really look for people who can make sense of an ambiguous situation, see patterns in, there's a fallacy that's called like seeing patterns in random noise, but doing that because the noise is not random, doing that in a non-fallacy way. And then lastly, I'll say like really caring about the outcome. We interview a lot of great software engineers, a lot of people who are really, really great coders, some better than, myself. And one thing that I see, especially younger people miss on sometimes, just because something is great code, like doesn't mean anyone cares about it. You should care about driving great outcomes. And good code obviously helps with that, but good code driving an outcome no one cares about, or good code driving an outcome that is, maybe not even a good outcome. Like that, there's no value to that. The outcome is what we care about. What drives like operational efficiency for our customers? What drives the people around Tally to love the robot and embrace it, as opposed to find it as a hostile entity? Um, what is the intent of this thing that we're building? What is the intent of the robot, and how can I contribute to that? Versus what's the most aesthetically pleasing code that will close this ticket for me?
Jem, thanks so much for taking the time. It's awesome to see, quote unquote, how the sausage is made at a company that's at a scaled fleet, and I'm sure many folks in the audience will, be listening here to get some insights on how they could do that for themselves. Before we end off, two quick questions. How can the audience help you? If you have any shout outs or call to action, feel free. And why do you love robotics?
Great last question. Thank you so much for having me, first off. How can people help us? We are hiring. We're hiring near and dear to my heart, obviously, as robotics software engineers, junior and senior, especially if you have experience working at a field deployed robotics company. We would love to hear from you. We're also hiring QA engineers and a few other roles. Please check out our careers page at simberobotics.com. And why do I love robotics? I've kind of always known that I wanted to do robotics, like from as early as like middle school. The thing that really does it for me is a lot of what we do as software engineers is very abstract, but robotics brings it into the real world in a very special way to me. It's like code that you can not touch, obviously, but it has a tangible impact on the world. That I find that very special and something that almost no other career, at least in like software, gives you. And that, yeah, that's why what I do.
Awesome. Cem, thank you again. This was a lot of fun, and take care.
Yeah, appreciate it. Thank you very much. Thanks for having me.